Okay, so we'll revise ensemble learning, and we looked at two main approaches to ensemble learning in the last lecture. We said that we're trying to solve two main problems. One is high bias, the other is high variance. How do we address the high variance problem using ensemble learning? How do we solve the high variance problem using ensemble learning? Anyone? Bagging. So we firstly said that ensemble methods are winning solution in a lot of Kaggle competitions. They work very well out of the box, generally work very well. The idea is to take multiple predictors and aggregate their predictions. We said that there are three main reasons why ensemble methods work. One is statistical reasons, which is there can be many competing hypotheses that you can learn on small amount of data, which we saw in the previous lecture also. We could have learned many decision trees which give the same accuracy on the train set. Second reason we looked at was computational. Many times the optimization algorithms that we use are greedy, are giving you local optima, so you're not able to find the global optima. And the third was representational. As an example, we saw for representational that if we look at depth 1 decision trees, they cannot learn these sophisticated decision boundaries required to do a good job at classification here, because they will only make a single axis parallel split, whereas if you look at random forest, you can get fairly good accuracy. Similarly, depth to tree, again it will make 2 splits, but again axis parallel splits. So decision trees with limited depth are very limited in the representation capabilities. We looked at the necessary and sufficient conditions for ensemble methods to work well. Does anyone remember these? Each of the member of the ensemble should be accurate, at least better than random, and they should be diverse. We looked at a quantitative perspective of if we have multiple members in the ensemble and each of them has certain low probability of being wrong, then probability that the majority of them are wrong is a very, very small number. But we said that this has a small flaw. What is the flaw in this argument? These calculations are based on the fact that each of the member of the ensemble is independent of the others, which is very rarely true. So first technique was to reduce variance, which is by bagging. What we did was to consider a data set and sample with replacement. So makes multiple smaller data sets by sampling with replacement from the original data set. And we looked at this example. If we looked at the different rounds, if we didn't do bagging, if we learned a complex decision tree on the overall data, we might get some, we can very clearly see it as overfitting through the data. But instead, if we had done bagging, so we look at 5 different rounds of data set, which is found by sampling with replacement. And if we learn complex decision trees on them, and if we aggregate the predictions, we can see that overall the variance has been reduced. Next, we looked at boosting, where the idea was, so bagging, you take a very sophisticated learner, you reduce the variance. Boosting, you take a weak learner, such as depth 0 or depth 1 decision tree, and you're trying to make it stronger by incrementally building over it. So we said that we give equal weightage to each of the points at starting. Then basically we want to give more weights to points which are misclassified and lesser weights to points which are correctly classified. We found out the fraction of the points which are misclassified. We call that as an error for the ith iteration, and we found out an alpha term corresponding to an ith iteration to be half log 1 minus error divided by error. And this alpha term also becomes a weight of the classifier at that stage, at iteration. We reweigh, so we can see that the points which were misclassified, the yellow points, their weight is increased. We also do a bit of normalization to ensure that the weights sum up to 1. And eventually, if we keep doing this, we will get multiple classifiers. In this case, I am showing 3 classifiers, 3 rounds of boosting done on this depth 1 tree. And finally, our prediction is summation alpha I x into the sign of the prediction. Okay, so today we'll be looking at a very popular ensemble method, which is known as random forest. So chances are, if you've used anything in sklearn and you've got good performance, or if you've heard of anyone using sklearn for competitions, many of them would have used random forest. So it's an ensemble of decision trees. It's a very specific kind of an ensemble built on top of trees. Now we look at two specific things done to random forest over decision trees to make them work well. One, you do bootstrap on the data, which means you look at the data and you divide it into multiple rounds with by sampling with replacement. Second, you do a random subspace of the features. Why do you think the latter makes sense? Random subspace of the feature means that instead of using all the features at any particular point, while we are trying to choose which attribute to choose to pick up in the tree next, we choose a random subspace of them. So folks, please do come on time. There's a lot of noise which comes when you shift your chairs. Unfortunately, I may have to close the doors at a certain point if this continues. All right. Why does it make sense to use a random subspace of the features, a random set of features? Anyone? The answer is right below the question that I'm answering. Okay. Say, Jadav. So if you choose so one of the key which you remember, we want to choose diverse members in an ensemble. One way to choose diversity or to force diversity is to give a different set of features at each stage. You don't allow the full set of features to be, so you don't want to be choosing from all the set of attributes, you choose from a random subset of the attributes. That will ensure that because of randomness, the different trees that you learn will be very different. The algorithm is quite simple. We'll be looking at, while there are a lot of parameters, hyperparameters associated with random forest, we'll be looking at the following. One, the number of trees which you use in the ensemble. Second, the number of features that you use. So number of features is typically denoted by M in this case. Maximum depth. What do you think number of features means? We are given a data set with some number of features. What does it mean to have a hyperparameter as the number of features?
So if we are given 7 attributes, we might only just operate on 5 or the 5 which are most
Right. So if we are given, no, not based on what is relevant, based on what is a random subset chosen. So you start with M features. Each stage, when you have to decide which attribute to split on, you use a subset of the features. And the subset of the features used is done randomly.
But it can happen. Let's say in the previous example which we were considering, we choose to play or not play. In that, if we're just seeing which parameter affects, which attribute affects the desired parameter, if you find that temperature is not that relevant, then is it not better for us to not even include parameter in our analysis list and just work on the other ones?
Okay. So Deep is asking an interesting question. He is saying that it seems that the temperature attribute is not particularly useful for the play tennis example, right? So he says that maybe you should just remove that attribute from the decision tree itself. Should we do that? Should we not do that? What do you think? Okay, so it's not a very trivial answer. If you know from domain expertise that a certain feature is useless, don't use it. If you don't use, that's the beauty of something like random forest. It will automatically do some feature selection for you. It will figure out which features are important, and we'll see in a few minutes how that happens. But the question here was the number of features. This is the available set of features you use in the decision tree algorithm to pick up the best attribute. Right? So if we have seen the decision tree algorithm, right? So we see this line. Pick up an attribute A from the list of attributes which best classifies the examples. So what we're saying is, instead of using all the possible available attributes, we do a pick up an attribute A from which is a subset of the total set of attributes. That is the change you'll have to make in the decision tree code while you're implementing ensemble methods.
From the subset, we choose the best one or just one?
From the subset, you choose the best one. If you do random there, then it's a very random IC algorithm. So mainly two steps. You build capital N trees. In each of the tree, you are doing bagging, which means you sample small n, you sample with replacement, the same data set size, right? And then you learn a decision tree on the selected samples from the ith round. Now, learning the decision tree for random forest is specific in this way that you select capital M from the total available capital M features, small m out of the total capital M features available, and train a decision tree on them. Any questions in this algorithm? Okay. So we'll be using this data set for today's class. This is known as the iris data set. This is a flower classification data set. We are having 3 species of flowers, and we have 4 attributes associated with the flower: sepal length, sepal width, petal length, petal width. If you remember your class 6th, 7th, 8th biology, you might have heard of these things. So if so as I said, that decision tree is an ensemble of, random forest is an ensemble of trees. So we look at a few trees being learned. So all of the trees are being learned. These following, I have looked at 10 different trees. So the first tree has a certain root node, petal width less than something. Entropy is something, number of samples, values, class is Vaginica. So this is basically what we've seen earlier, nothing new in this. We learn multiple decision trees. So if I go over them again, just notice how just look at the root node in each. First one, root node is petal width less than 0.75, petal width less than 0.8, similar. Sepal length less than 5.55, sepal length less than 5.55, again same. Petal width, petal width, petal width, petal length, petal width, petal length. So do you see that the petal length comes a lot as the root node? What do you think that means? Across the 10 trees we have seen, probably in around 5 of them, we saw petal length as the root node. So the attribute petal length is probably the most informative. That's why it's chosen as the first stage, as the root node in many of the times. Sepal length or sepal length or sepal width. Sepal length also occurs quite a few number of times, which means it's also an important attribute. There are some attributes which don't occur at all, which means they're likely to be less important. And eventually you can do something like this. So random forests give you a method known as feature importances, and here overall we'll see that this is normalized to sum to 1. Petal width, petal length, sepal length turn out to be the 4 features, out of which petal width, petal length are the more important ones. Now the question is, how do we compute this feature importance? This becomes very useful in interpreting your results. I've just given you a hint. The root node seems to be a more important node compared to the others. Why is that? It gives us good amount of information gain. That's one aspect to it. What could be some other aspect? It also looks at the maximum number of samples. So it's giving you information gain over a large number of samples. It's reducing confusion over a large number of samples. Therefore, it's more important than maybe the other nodes which have the same information gain. So now we look at this complicated looking formula, and then we'll write code to understand this. So today's class will be a mix of lecture and tutorial. Psi 1 through psi m, capital M, are the M trees that you have learned. So I want to compute the feature importance of a variable x underscore j. In our example, x underscore j could mean petal length, petal width, sepal length, sepal width. Right? So xj, think of this as being indexed from 1 through 4. Capital M trees, in our case we had 10 trees. Psi m, or whatever the symbol is, it is the mth tree. You want to find out the importance of the xjth variable, sepal width variable, let's say. So you first do 1 over m, and you are computing something over the M tree. So can you see that you are finding out the variable importance by doing some operations which is averaged over the M trees, right? So which would mean that if we can understand the inner loop, we can just compute this inner loop quantity over each tree and then find out the overall importance, or rather just find out the importance of a variable in the ith tree, in the mth tree, and then aggregate it over the capital M trees. Right, let me repeat that. So this inner loop finds out the importance of the jth variable in a single tree, and then you aggregate or average the importance of a single variable across the capital M trees. Right. So you have to look at delta IT is impurity reduction at node T. Impurity reduction you could think of just as information gain. So delta I of T is the entropy or the information content associated at a specific node T minus the fraction of nodes going to the left part of the tree and the fraction of nodes going to the right part of the tree. That is the weight used for the information in the or the entropy of the left of the examples left in the left subtree and the examples left in the right subtree. Right? This is the same information gain which you are coding in your first assignment. You divide your data set into left subtree and a right subtree, which means you divide them into some number of examples. You find out the entropy of the overall set, and you then find out the weighted entropy of the two subsets in which you have divided. So this part is easy, we have seen this earlier, but we have another factor P of t, which is known as nt over n. Capital N is the total number of examples that you will see in the tree, right? Nt is the number of samples the tth node is seeing, right? So up in the root node, what is nt? N. For the root node, you are seeing all the examples, right? So therefore the fraction of examples you are seeing is 1. For the bottom nodes, for the nodes fairly down in the tree, the fraction of points that you are seeing is low. So think of this scenario, the information gain that you get at the root node and at, let's say, the second last layer depth is the same. Which of them will be more important? So you have two variables. Let's say sepal length or let's say petal length is the root node here, and let's say sepal length is over here. It's the second last layer. Both of them give you the same information gain. Which of them would you consider to be more important? The root node. Why? Because it is giving you that information gain over a much larger fraction of the examples, which is where this formula of Pt equal to Nt over N is coming in from. Yes. How the formula? Pt. Pt is the fraction of points, which fraction of samples you are considering you are viewing at the tth node, right? So let's say at the root node, let's say the root node is t equal to 0. How many points will you be looking at that root node? All the points, nt equal to n. Whereas at this node, the number of points, the fraction of points you would be looking, which will be left, would be a much smaller number. So therefore, even if you get the same information gain for two nodes at different depths, you'll have to weigh them by the fraction of points that they are giving the information gain over. Okay, what does 1 jt equal to j mean? Does anyone know this notation? Sorry? It's an indicator function, jt equal to j. So this will be returning a 1 when jt equal to j, and it will be returning a 0 otherwise. Right? So it's a sophisticated way, it's a mathematical way to write this. We'll be looking at this at a programming sense, it will probably be easier for you to understand. Okay, any questions in this formula? It will become clear once we try to implement this from scratch. So this is the final outcome that we want. We want to say that out of the 4 features, how many of which of them are more important, which is being calculated using this formula or some similar formula to this. So let's do some amount of coding. I will specifically disable Copilot to show how to go about such exercises. Is the font size clear enough? Should I make it slightly bigger or is it clear enough? Clear enough? Okay. So I'm showing you the iris data set. You can notice that there are 150 rows and 5 columns. The final one is the species. So it's the species can take 3 different values. So it's a classification problem. The inputs are real. So real inputs and classification. Real input, discrete output kind of a problem. We can see the unique classes in the data set. Setosa, versicolor, virginica. So this data set, if you notice carefully, what can you see in the species columns? Can you notice that they're ordered? The first 50 examples are all Setosa, the next are all versicolor, and the next are all virginica. Right? So therefore, it always makes sense to shuffle your data. Another very useful exercise is to make something known as a pair plot. So pair plot is looking at all pairs of features. We have 4 features, so we're looking at 4 C2 combinations like sepal length and sepal length. So what do you think sepal length and sepal length is showing? What do you think this diagram is showing you? X-axis is sepal length, y-axis is also sepal length.
I think it's the program.
So this is showing you the density of the points across the 3 classes. If you notice the classes colors, Setosa, versicolor, virginica. Right? So what it is saying is that Setosa has, if we go back and look at this, Setosa generally has a sepal length of 5 or so. Right? It's centered around the sepal length of 5, whereas virginica seems to have a higher mean. Right? All of them almost look like normal distributions with different amount of variance, and we can see that the sepal length for virginica seems to be much higher. Right? Why do you think this is a useful exercise? Do you not have a chair there? There's one chair here. If you want. Middle column, 3rd row. There's a chair here.
It can help us verify if the different ways in which we have divided data is actually random, it has gotten less biased.
Yeah. So let's think of this as you're doing some exploratory data analysis. Forget about doing sophisticated machine learning algorithms in the first stage. Can you just look at this plot and say that, rather just look at this plot, petal length, right? Can you see that petal length seems to very clearly distinguish between the 3 classes? So for example, petal length for the Setosa class is always less than 2.5. There is some confusion in between the virginica and versicolor, but in terms of Setosa class, it's very clear. So therefore, making such distributions is usually useful across the 3 different classes. Okay. What do you think this diagram is showing? This is a scatter plot between two features, sepal length and sepal width. Can you see that at least this blue color class is very clearly separable? You could just draw a line and you could separate out between the three classes. This one is very easy to do. And if you look at sepal length and petal length, does it seem like these are two of the better features? So there is very less confusion between the three classes or three clusters of points. So therefore, I always recommend for such kinds of problems you make these pair plots initially to get a better sense of the data. Now we'll do the usual, divide your data set into X and Y, fit a random forest. We'll come back to this attribute, so notice this carefully, bootstrap equal to true. And rf.fit X and Y, the number of estimators I've kept to be 10, the criterion I'm using is entropy, this is not the default, I think the default is probably gene index. So I can now create these different trees. I'm plotting each of these trees. This is the same tree which you saw in the slide. If you notice the default tree, it does not give you so much of information, right? So we had specifically made certain changes here to this function. So I did command click, and in Windows you can do I think control click to open the documentation for a particular function. They have certain input parameters such as the out file max depth, feature names, class names, label field, impurity equal to true, node IDs equal to false. Node IDs are typically not shown. I am showing the node IDs so that you get a sense of how the tree is implemented. And you'll get a much better sense of why scikit-learn team has chosen certain ways of implementing it. It's a very good design. So it's a design which has lasted the test of time. So I think scikit-learn was probably launched in the late 2000s, 2009, something around that. And it's been a benchmark of machine learning software since then. So let's look at this tree. Look at the node numbering. So 0 has children 1 and 2, 2 has children 3 and 8, and 3 has children 4 and 5, 8 has children 9 and 10. So this I leave to you as an exercise as to why sklearn might have implementing the node ordering in this way. Why does 3 have children 4 and 5, or 2 has children 3 and 8, not 3 and 4? You have to think about this. If you already know, you know. If you don't know, think about this. Why sklearn might have decided for this kind of a design. It's very thoughtful. It's not randomly chosen. If you understand this, you'll do better in your interviews also, where you're asked to, let's say, invert binary trees, things like that. So the total number of samples in our data set was, does anyone remember? 150. Good. At least some of you are awake. The total number of samples was 150. The number of samples here is 94. What is going wrong? Have we made a mistake? Has sklearn's implementation made a mistake? Or are we missing something?
Have we divided it into training and testing data?
We are using currently all the 150 examples for training. Sorry? No. So this is not subset of points where petal width is less than 0.75. So each node shows the total number of samples it has considered.
The tree will pick some random samples. The tree will pick some random samples and train on that. So every
Can you use, so Jadhav says the tree will pick up some random samples. Can you use a more technical term?
we saw that boosting is
Sorry, you said something, yeah? Bagging. So if you remember just a few seconds back, I told you this. Notice this parameter, bootstrap equal to true. But why do we get 94 samples out of 150? If you're doing sampling with replacement, doesn't this seem like a very small number? Should you not be getting something close to 130, 140? Why do we get 94? So 94 here means 94 unique samples. Some samples will get repeated. Why do we get 94? what is the expected number of samples when you do sampling with replacement? Expected number of unique samples. Does anyone know this? Okay, let me. So we had one. So if I do 1 minus 1 over E, where E is the 2.7 constant, and do you see this number is fairly close? Right. So the expected number of samples when you do sampling with replacement or you do a round of bagging for n is 1 minus 1 over E into n. I've asked this question previously, so again telling you to prove this. Right. You can do this as a homework exercise to prove that 1 minus 1 over E is n to n is the expected number of samples when you do sampling with replacement. So therefore, you don't have 150 samples at the root node, you have 94 samples, which 94 unique samples. What do you think the value means? 47, 44, 59. You have 3 classes and this is the number of samples you're predicting for each of them. Okay, entropy is 1.573. Is this entropy calculated for 150 examples or 94 examples? 94 examples, because that is what is getting passed onto the tree. You can also verify this. So I would always encourage you to do such kinds of exercises. Look at the argument, set the argument to be false, bootstrap equal to false. If our understanding is correct, we should be seeing 150 samples now, and the entropy to be slightly different number. Samples equal to 150, entropy equal to 1.585. Right? So we verified that using the bootstrap does make a difference. And the tree is now consequently bigger because now you're processing higher number of samples. One of the reasons could be that. I wanted to show.
Values are predicted because they did not sum up to 92.
The values are?
Are the values?
Okay, let's go back and set the argument to bootstrap equal to true. Okay, what do the values sum up to? 150. Previously also the values sum up to 150. So these values means that they are prediction over the entire set. Right? So these are all good observations. You should be thinking about why they have made such decisions. These are the predictions you see at the root node. The majority is 59 predictions are for Virginica, third class. Therefore, the majority here is Virginica. What do you think about the colors? This one is light purple. This one is slightly darker purple. This one is even darker purple. Why is this?
Maybe because of the purity of it.
So the purple is indicating the Virginica class. And here it's, so wherever you see completely Virginica class, only Virginica class, that is dark purple, whereas this one is very light purple to show that not all the samples are purple. Right? Again, beautiful design in terms of, so you just need to look at the colors and you'll get a very good sense of how the tree has been built, the purity of the samples he was talking. Similarly, Setosa seems to be dark orange. Here versicolor is almost completely green. I don't have any light green colors to show the variance. Okay, so how do you think sklearn would have kept the different decision trees in the random forest? Random forest is a collection of trees, right? How would you store that collection? What is the natural data structure you would store a collection? Now this again becomes important from, let's say, understanding the coding perspective. Also, let's say if you have to design, if someone asks you a systems design question or an algorithm design question. What could be a good data structure to store multiple trees in a random forest? How do you store collection of objects in Python? In a list? Why not a NumPy array here? Would it be useful to have a NumPy array of decision trees? There's no benefit you get by that. So list would suffice, and that's what they have done. So I have now turned off my Copilot, and you'll see that if I do rf dot, it gives me various fields and methods which exist. So this one looks interesting, estimators. So I'll just click on this and see what I get. rf.estimators underscore gives me a list whose size seems to be 10. Each of them are using some different random state. The criterion in each of them is entropy. The max features in each of them is square root. What do you think max features equal to square root means? So we had a total capital M features. It is using square root M as the number of random features you'll choose at each stage. So again, you can look up the detailed documentation and see why they might have done it this way. But the important thing you can notice here is that rf.estimators underscore gives you a list of trees. Right?
What does random state mean?
Random state, I think, is just the random seed with which it's starting. The random seed will get used everywhere in the experiment. As an example, when you are doing a random subset of the features, you will have to use the random state. But again, a good question, you can go into detail and figure out whether this is a random seed or whether this is something coming in from a pseudo random number generation algorithm. So first, let me actually show you so we want to look at the feature importance, right? So if I do feature importances, I get a list, right, which is 0.09, 0.03, 0.32, 0.544. This is corresponding to the 4 features that I had, right. Now this is what we'll want to somehow create. Now if you notice in the code that I had shown you, I had told you that you should always consider simplifying the results. So let's just look at the inner loop. Can we find out a feature importance for each tree and then just aggregate it? Right? That's what this loop is doing. Importance for a variable is the aggregation over the feature importance of that feature over the different trees. Right? So let's do that exercise over here. So rf.estimators is giving me trees. So let's just pick up the 0th tree, which is the first decision tree. It is a decision tree classifier with something something. So let me just call that tree 0 is this. And if I look at tree 0 dot feature importances, can you see that tree 0 also has a feature importances? For each of the tree also I can compute the feature importances. Now can I just loop over the trees for tree in rf dot estimators, and let's just call the overall s to be empty, s dot append tree dot feature importances. So for each tree I calculated feature importance. If I look at s, it will be a list of arrays. I can do an np dot array of s. I get, if you look at the shape, 10, 4. So 10 trees, 4 features. I can calculate a mean. I get a single number, 0.25. But I can calculate it over a specific axis, and I get these numbers. 0.098. Does it match what we saw in rf.feature importances? So does this mean that you have solved one level of complexity? Right? Now, if you can just figure out how to compute the feature importance for a tree, you can just easily compute the feature importance for random forest. Right? So this is the way I want all of you to think. Whenever you are given a more difficult problem, can you break it down into simpler problems and then just compute the aggregation over them? Now computing the importance over a tree is fairly sophisticated. So I'll want all of you to be more aware. I understand the 8:30 a.m. lecture and the tiredness associated with waking up early, but if you can try, and also in the interest of your friends, if you want to just wake them up. So this is the mapping which is being used for feature names to feature indices in the feature importance. Right. So 0 is for sepal length, 1 is for sepal width, 2 is for petal length, 3 is for petal width. And you'll also notice that this is the same as the list of the columns which we had. sklearn also uses something else. Sometimes when we have leaf nodes, like this is a leaf node. I'll say leaf node as a node which doesn't have any children. Right. So this is a leaf node. For it, we will be using a different mapping. So I've got one tree, right? Let me show this. This tree I already had. I can do tree dot feature, right? I've just written tree dot feature. It gives me 3 minus 2, 2, 3 minus 2, 1, so on and so forth, right? But we said that we have 4 features, 0, 1, 2, 3, and then we have something minus 2, which I am storing as a leaf node, right? That's some sklearn convention. This is telling me the feature which is being used. So let's look at node 0, right? Node 0, what is the feature being used? Petal width. And if I look at node 0, petal width. Node 1, it is a leaf node, doesn't have any children. If I look at node 1 dot feature, it is minus 2. Minus 2 means that there is no child of this node. Right. Similarly, for node 0, 1, 2, node 2, the feature which is being used is feature 2. Node 2, feature which is used is feature 2, which is petal length. Right. So therefore, we have 13 nodes, out of which we have a few leaf nodes, and a few of them are split on certain attributes, which we are able to get by this. Why are we using this function? Why do I need to know which feature is being used at which node? What was the aim of this experiment? We want to find out the feature importance. The feature importance we've seen is you have to find jt equal to j. You have to find out which feature is being used at which node. That information you need to know. So therefore, we have written some code to figure out the node, the feature being used at any particular node. So we'll be using this further in the tree. What else do we need to compute the feature importance? So let's look at the formula again. What else do we need? We need to know pt, which is a fraction of points that we are seeing. We also need to know delta it. Right. For delta it, I need to know the information in my left tree, and I need to know my information in the right tree. So therefore, I need to know the left subtree and a right subtree, and I have to have some feature which I get out of them, some function which I apply to them to get something, to get the information content. So then I've created, so then there is another useful attribute dot children left. And children right. Okay. Node 0. What is the ID of the left child? 1. What is the ID of the right child? 2. Look at this code. Tree.children left for the 0th node is ID 1. Tree.children right for the ID 0 is ID 2. Right. Similarly, for ID 1, minus 1, minus 1. For ID 1, does it have a left child? No. Does it have a right child? No. So whenever it doesn't have any left or right child, you are given minus 1. Right. So for node 2, the two children IDs are 3 and 8. 3 and 8. Right. So, we have just confirmed that we are able to get the IDs of the left child and the right child. We will be further using these IDs in order to compute the information gain. So, I have this function print child ID given a tree and a node. I can show this for the different entities. Now, I want to be computing the information gain. So, no laptop policy. Okay. We want to be computing the information gain via this formula. So, we need to be computing the entropy of the ith node of the tth node and the entropy of the left child and the right child. So, let us see how we will do that in code. Firstly, I need to get the left and right child of a given node. Given the tree and a node ID, I want to get the left and the right child. Then interestingly, so if I look at tree dot impurity, impurity of the 0th node is 1.573. You go back to the tree, impurity of the or entropy of the 0th node is 1.573, impurity of the first node is 0 and 0.985 and then 1.65. So, the sequence which we are looking for is 1.573, 0, 0.985, 0.348. We will verify if that is the case. 1.573, 0, 0.98, 0.347. Right. So, therefore, we get access to the impurity for each node, which is again a beautiful design by sklearn teams that they are able to store it in a node wise fashion, so that when we need to use them, we can have ready access to them in a very ordered fashion. So, I can calculate the entropy of the entire node as tree dot impurity of node. I can calculate, so by left and right child function, I get the left and right child, I can calculate their impurities and I can also calculate the entropy of the left and right. There is a variable called n underscore node underscore samples. 0 means for the root node. This is the total number of samples which the tree is seeing. In this case, what is capital N? 150 or 94? 94. We are seeing capital N equal to 94 samples, which we will use in this tree. Number of samples which are in the left node is n node samples of left, n node samples of right. So, if you have ever written any tree like algorithms, this is showing you the recursive structure of it. The number of node samples in the left part of the tree, number of node samples in the right part of the tree, where left and right are just the indices being used. The total number of nodes which the number of samples at this specific node is NL, number of nodes in the left and number of nodes in the right. So, then I can calculate the information gain at the Tth node using the simple formula which we have seen. Entropy of the current node minus entropy of the left node minus entropy of the right node, but these left and right entropies need to be weighted by NL over NL plus NR and NR divided by NL plus NR, which is a fraction. So, that is exactly what we are doing. Entropy of the node minus NL over NT into entropy left plus NR over NT into entropy right. And then finally, from this function, what I am returning is the information gain, the total number of samples N, the number of samples going to the left part of the tree NL, number of samples going to the right part of the tree NR, and T, which is NL plus NR, and the feature which is used at the Tth node. So, at this stage, we need to iterate over each and every node. Right? I will get the feature used, the NT, NL, all of this information gain. I can calculate PT, which was NT over N. PT is NT over N. I can calculate that. I can put a score of a feature as the default is 0 plus PT into information gain. Why are we not counting the root node in the NT? I didn't get the question. So, capital for the root node, capital N will be NT. Both of them will be the same. The root node is considering all the samples.
We are traversing in a node.
Yes.
And we are calculating the total childs in the left part and the right part. Why not the root?
There will be the sum. So, each parent will divide the data into samples, which will be the sum of the children's samples. So this is the main formula. Score for a feature is the score for the feature of or default of 0 plus the PT, which is a fraction of points seen at that node, into information gain. So it's a very succinct way of writing this. Finally, if I calculate, okay, I get these values. So I get the scores over each of the tree, and then I do the normalization, and then I'm storing them in the descending order. They seem to be giving me almost comparable results to what sklearn does, but maybe there is some slight difference in the way sklearn is implemented this. Therefore, or there is a small bug in the code which you are free to find. So, in essence, through this exercise, what I wanted to show was that you can hack through the code. You can also look into the, let's say if I go into the RF, where I have defined RF, right, RF.fit. So firstly, when I started this exercise yesterday, I was not sure where the number of samples is getting reduced. So I went into this. Initially, if you look at the code, there are a lot of checks, which is the feature of very good code bases. They'll have a lot of checks. It looks at some criterion. It has this function. If so, n samples bootstrap equal to get underscore n underscore samples bootstrap, n samples equal to x dot shape 0, max samples equal to self dot max samples. So this function will get you the bootstrap samples which you will be using. If you want to go further, you can do control click here and look at the number of samples in a bootstrap sample. So as you'd expect, it will be using an interval between 0 and 1. It will be doing a uniform sampling over that and then picking up the samples. Good. Any question in this lecture on finding the feature importances? Okay. So we'll then go on to the next topic. How many of you have used something known as Meshgrid in Python? How many of you use contour plots? Okay. So this is also going to be a programming exercise. It's a slightly difficult concept. Like you can always use some ready-made code, but I wanted to go through this code so that you get a much better understanding. This one. So sepal length and sepal length, right? So if you look at just sepal length and sepal length, you will be looking at basically looking at a single variable. So I can actually show this better. So let's look at iris. Our data set iris contains these columns. Let's just look at iris dot sepal length. It is these few values. I can do a histogram over this, right? So it gives me histogram, or I can make a continuous version of this. Okay, so I think the way to give KD plot is slightly different. Maybe dist plot. Okay, this is deprecated. Okay, I don't remember the argument, but let's look at cborn and dist plot. Kind equal to KDE. Data should be a pandas data frame. That's what I've done. Data equal to penguins, x equal to this. Okay. sepal length. Multidimensional indexing is no longer supported. Okay, I don't know why for KD it's giving this error. Yeah, so this should be a NumPy array already, dot values. But SNS.kde plot should have also worked. KD plots wants data and x equal to something. So data equal to iris x to sepal length. Multidimensional indexing is no longer supported. Yeah, so just think of, I don't know, this particular error. Object colon none is not supported. Yeah, essentially what you want to do is to make a smooth version of this histograms, right? The histograms which you saw here. No, not these many. So let's assume you had a smoother version of this being done, but you had also done that on a group basis. So you had 3 different groups. You had sepal width, so you had iris data corresponding to setosa, versicolor, virginica. For each of the group, if you plotted the sepal width, histograms for them, how would they look like? So that is what this plot is showing you. This is showing me the histogram or the smoother version of it, which is known as KD plot, density plot, or think of this as an approximation to the probability density function. So it's clearly showing, let's look at this one, that most of the points for setosa have this mean and mean to be around 2. Right. The other way to look at this is you can always do a group by operation and you can compute some statistics. So iris dot group by on the species, this will give you a group by object of sepal length dot mean. So sepal length you can clearly see if you just look at the means. Setosa 5, versicolor 5.9 and virginica 6.58. The petal length was the one which we were looking at. Right. So you can see that they're clearly separated out if you look at the means of these features for the different classes. So therefore, if you just look at the petal length feature, you should be able to distinguish between many of the samples in this. That's what it means by looking at these histograms. Other questions? Yes. Okay. So as I discussed, let's now look at the next topic, which is known as contour plots.
Just on this, so when we are looking at, let's say, 2 same variables, can you say that we can use that to find the root node?
You can, so if you look at this way, you should be able to match your intuition as to what the root node might be, or what an important feature is, or what feature helps you very clearly classify or distinguish between the different classes. That's the overall objective, right? If you can understand, this is what we have asked you in the assignment. Can you look at the accelerometer data readings and figure out if you can see the distinction between the classes, which is expected that you'll see that perhaps for activities like jumping, running, the accelerometer data readings have to be higher. Right? They'll show more acceleration. So the question was, can you just look at the raw acceleration values and separate out the different classes? Similarly, can you just look at one of the feature and just separate out the two classes without using any sophisticated machine learning algorithm? The simplest algorithm, machine learning algorithm you can use is like a decision tree, which is what I'm asking you to do. If you can just separate out on the threshold of values. Okay. No, not this one. I'll show. So I'll now show that if we have to make certain predictions over an entire decision surface, which is very common. So if this is my data set, I use a random forest to fit over this data, and then very often in my slides you might have seen I'm using something like this diagram, right. So this is now indicating the probability of class 1, right. Probability of class 1, it's almost 0 in this region. Class 1 is the yellow class. Probability of class 1 is 1 here. Probability of class 1 is very low in this region, and probability of class 1 is about 0.5 in this region where you have the decision boundary. So how do we create such a diagram? What do you think? How might I go about creating a map, a diagram which looks like this? I gave the hint earlier, something known as contour plots, but you may or may not have heard of that term. So think in simpler terms. Can you divide this entire region into a grid? On each of the grid point, can you tell the prediction? rf.predict, that is all you need to do. So that's what we'll do, and then we'll see a sophisticated way of doing that. We'll be making use of something known as Meshgrid. So let's assume that we had two arrays. The first array is 1, 2, 3, 4. The second array is 5, 6, 7. I call this np.meshgrid on x array comma y array. I get two arrays in response. I'll typically call them xx and yy. That's what the general convention is. What do you think these are returning? What is happening in this function? Sorry? Broadcasting, repeating, right? So the 1, 2, 3, 4 x array has been repeated how many times? 3 times, because the length of the y array was 3. Similarly, the 5, 6, 7 has been repeated how many times? 4 times. So therefore, the entry which was 4, comma 1 has been now converted into 3, comma 4. And this has also been converted to 3, comma 4. If I look at the shapes, both of them are 3, comma 4, which is expected. Now, I basically wanted to pick up from this point, from these two arrays, I wanted to consider various possible combinations of a grid, right. So what I wanted to say was, this is my x dimension, where I have points 1, 2, 3, 4, and my y dimension is 5, 6, 7. I wanted to pick up all pair of points 1 5, 1 6, 1 7, 2 5, 2 6, 2 7, 3 5, 3 6, 3 7, 4 5, 4 6, 4 7. To facilitate that, this particular function exists. Now, can you look at these two matrices xx and yy and tell me how would I get this 1 5, 1 6, 1 7, 2 5, 2 6, 2 7, 3 5, 3 6, 3 7, 4 5, 4 6, 4 7. How can I index and get these values? So let's assume we loop over these. For I in range, the first I in range 3 and j in range 4, we will get the ith value to be I, jth value to be j, and then we'll pick up xx of ij and yy of ij. If I do that, and I create this data frame, can you see that at the 0th position, I get entry 1, 5. At 0th, 1th position, I get 2, 5, 3, 5, 4, 5, 1, 6, 2, 6, 3, 6, 4, 5, 6, 1, 7, 2, 7, 3, 7, 4, 7. Right? So, total how many grid points will we get out of an array 4 in the x-axis and 3 in the y-axis? How many grid points will we get? 12. Can you confirm that we have 12 entries? Right? So, this is a way to get all of these entries, right? To create this grid-like structure. You could have done it other way also, but we'll see why this makes sense few minutes down the line. So, I can also plot xx and yy, right? So, then I get all of these grid points, which is what we wanted, right? So, finally, we will want to plot or we will want to calculate our prediction at each of the grid point. So, now I will do this same example, but over a bigger grid. Currently, my grid is just 12 points. I will want to now look at a bigger grid so that I can create a diagram like this. So, I will use, I have two features, x of 0 and x of 1. I will be looking at the minimum value in my data and I will be looking at the maximum value in my data in both these features and just take slightly beyond both these ranges. So, I will do x lim is x of 0. So, the first feature minus 0.5 and first feature plus 0.5 with the data, and then I will create a grid. So, similar to the previous grid, now I will have a grid in the x axis, the line in the x axis and a line in the y axis, right, along the y axis, and for each of them I am using 30 points. If you want this to be a better, more higher resolution figure, you can just increase this 30 to 50 or 70, 100, whatever. It will become slower, but the plots would be smoother. Right. So, I have done that and I am now showing you all the points 30 cross 30, 900 points in this array. Now, what I can do is I can pick up an ith and jth index and I can get the point x point comma y point, right. So, in this case x point is minus 2, y point is minus 2, something like that, and I can use my models to predict the probability of class 1. This is a inbuilt function in random forest, predict proba, or you could have just predicted the class. In this case, I am predicting the probability. And you can see that as I vary I, what changes? As I vary I, you can see how the probability of class 1 changes, and now I am moving across this space. Similarly, if I move in the other dimension, you can see how the probability will become now very high of class 1, whereas if I move to the other extreme, probability of class 1 is very low, right. So, effectively I have now created 900 points along this 2D grid. I flattened them into 900 points and I can evaluate my prediction at each of them. So, that is what I will do. I am showing you xx of 0 and yy of the first column. So, as I had done previously, or actually if you know that my sklearn model always wants the data in this format, first feature, second feature, right, or number of features. So, number of rows comma number of features. How many rows should I have in my new data set in which I am plotting over this grid? 30 cross 30, 900. Corresponding to these 900 points, I will have an x dimension and I have a y dimension. So, what should be the dimension of my data over which I want to predict? 900 comma 2. But I currently have a 30 comma, I have two arrays of 30 comma 30, right. I do not have a 900 comma 2, I have two arrays of 30 comma 30, which I will have to reshape into this shape of 900 comma 2. So, I will start with the XX array, the shape of that is 30 comma 30. I can flatten it using something known as a Ravel function. The shape then becomes 900 comma, or it is a 1D vector. I will also highly encourage everyone to use these operations known as INOPS. Does anyone know what INOPS stands for? Anyone from the physics background here? Anyone knows any famous scientist in physics who's done Einstein? So this is Einstein notation to look at high dimensional tensors and do certain operations on them. And it's very intuitive. So I have my XX matrix whose size is ij, I and j both are 30. I contract it to a shape of I into j and then 1. So it becomes 900, 1. Similarly, I do for the, I could have also removed that 1 at the end and I would have got a 900, shape. The reason I am doing this, if you remember, is I want to get a matrix of size 900 rows and 2 columns. So I can do the similar thing for YY. I'll call these matrices as XX flat, YY flat, and I can also then put them both together. So then I'll get 2 matrices of size 900, 1. But I wanted a matrix of size 900, 2. Therefore, I can again call the Einstein operation, Einstein ops, to rearrange from number of features f, number of samples n into size 1, which is f is 2, n is 900 and 1 is 1. I can reshape this to n, f. So if I reshape this, I get 900, 2. I could have also done it in some other ways, using something known as numpy.hstack, numpy.vstack. I'd highly encourage you to try out both the ways, specifically using Einstein operations like methods, because they work across TensorFlow, PyTorch, NumPy, JAX, all of them. Whereas if you don't use such libraries, you may have to look at different methods in let's say Torch, which may require you to do something like stack or concat. In NumPy, there may be some other method like hstack, vstack. How 902, 2 came? So we started with 30, 30. We first reshaped. So think of I to be 30, j to be 30. I reshaped that into I into j, 1. So that became 900, 1. Similarly, for YY, I did the same. I get another 900, 1. So now I have 2 matrices of size 900, 1. If I just lay them flat and I create a NumPy array out of them, the shape I guess is 2 matrices of size 900, 1. Now I want to reshape this to 900, 2. I could have used something known as permute the axis, transpose, pick up a certain axis, do all of those things, but I would always encourage to do something like this, which makes it very clear as to what the operation are you doing. I'll call f to be 2, the number of features, n to be the number of points 900 and 1 to be 1. So my input is of size number of features, number of points 1. I want to reshape this to number of features, so number of points, number of features f. If I do this, my data is reshaped into 900, 2. So now once I have this 900, 2 matrix, you can also very carefully see the first 32 points. You can see that this is effectively what we'd seen earlier in the Meshgrid like setup. Minus 1.6, minus 1.2. So minus 1.2 is common for the first 30 points. For the next 2 points, this is now minus 1.3, and you're seeing this being repeated now. So out of, for these 900, 2 points, I can get the prediction for the 900, 2 input points, which will be a 900 vector, length vector. If I get that vector, I can now make a scatter plot with XX flat, YY flat. So this is of size 900, this is of size 900, and C color is also 900 element vector. I'm using a C map. Does this look like what? Does this look like the plot I had shown initially? Yes? Just looks like a more discretized version of this, a poor version of this. But this is effectively how such things are computed. And I can do something smarter without using something known as contour. I'll start with this image. So using this image, can you make it smoother? How would you go about that? So this task in machine learning is also known as super resolution. You start with a lower resolution image. This time it's 30, 30. How would you make it 60, 60? So you have two grid points. Let's say you pick up these 2 points. How will you fill an entry between them? You can do, if you do an average over them, that's linear interpolation. You could do some non-linear interpolations also, like fit a spline or fit a neural network to it. Right? You can do arbitrarily complex things. This is used a lot in various kinds of things. So we can start with this. I can also do something like interpolation. In this case, I'm using a spline interpolation. I get a diagram like this. But here I'd shown you something else initially. What is the difference? One, this looks prettier. What is the other more informative thing that you're getting in this plot? There is a color bar which has an attached meaning to it. Can you see that there are different lines? What do you think those lines or locus means? So this particular, the darkest line here, so in fact here I've divided into 10 levels. Let me show that code first. So I've explicitly divided this plot into 10 different levels of probability of class 1, 0 to 0.1, 0.1 to 0.2, so on and so forth. Right? Now all the values which are lying between 0.9 and 0.1 will be colored in this specific color, and then therefore you can see these specific locus. Right? So these are known as the different levels in the contour plot. A contour plot is typically used, you might have seen in war movies, where they have to scale some mountain. They have that surface plot, they have that mountain, and they view it from the top. If you view a surface, 3D surface from the top, you can look at the lines where the z value is the same or the height is the same. So this is indicating where probability of class 1 equal to this value between this and so on and so forth. So that's how you have divided into this data. To get this plot, all I had to do was call this function contour of f. F means filled. If I remove f, it will just make contoured lines, but I can do contour filled. XX was that array 3030, YY array 3030, Z was the array 900, 1. I can reshape that to 3030. That's the format in which contour f works. And then I can give a color map, some number of levels. If I reduce the number of levels, you can see how it will change. Just 2 levels, just 3 levels. If I make it a lot of levels, it will now, if you notice, it looks not very different from the above image that I had created using interpolation. So in the next class, before the next class actually, let me show you the final thing. We can also use a contour plot to create surfaces like this. I wanted to plot this function x square plus y square over a grid. So over a 3D diagram, it looks like this. Right? Now think of a contour map as cutting parallel lines over this space. Right? So this axis is the z axis. So what would z equal to 20 look like? It's a plane parallel to the xy plane, but if you view from the top, will it be a circle? Right? You've made a cut in this 3D bowl, and that's what this is showing. Z equal to 20 would be a circle, z equal to 24 would be a circle, so on and so forth. So this plot also I obtained using contour maps. More details I'll show in the next lecture of how contour works, and then we'll begin with linear regression. Thank you.